All righty. Hello there, class. All right, we're ready to rock. We still have some problems to work out of the section in Chapter 2 where we're doing even and odd, rational, irrational, floor, and all that kind of mess. But hopefully next time we'll cycle through the rest of those problems. What I'd like to do is set up what we'll be doing after that, and that is some proofs involving sets and set operations. I suspect that if you've survived math classes up until this stage, you probably are familiar with some of the things I'm going to tell you today. That's fine. What I really want to get to is, okay, then how do we construct proofs where we have these operations with sets appearing? And that's going to be the real focus of what we do. But we have to start, just like we did last time, with some basic definitions, and then we'll build on to that. So let's start with some sets. Let A and B be sets. By the way, I've kind of figured out, I think, that working while sitting down and having the tablet here, not having to get out of the way to rig things up to where I can reach it, is going to work much better. But we'll see. I think it'll lead to neater handwriting on my part. Let's let A and B be sets. And let U be a so-called universal set that contains both. Now, and I might as well go through and talk a little bit about notation here. What we mean by this is that A is a subset of U and B is a subset of U. Okay, just to kind of flash up the notation. It's very much like less than or equal to. It's just that you're using a sideways. There's no points on it there. Okay, so that's the subset symbol. So let's start with a definition. The union of sets A and B denoted A, and we use it looks like a smaller U like this, okay, but it's easy to remember because U, union, this is the set of elements in set A set B or both. Okay, so if I'm wanting to illustrate that, a common way to do that is with a Venn diagram. Where that represents the entire set, universal set U, and then we use overlapping circles to represent the sets A and B. So when I'm talking about the union, I'm talking about everything in the set A, so that's all of this, Okay. Or in the set B, okay, or both. So that stuff in the middle is actually in both. So the whole thing then is the intersection. I'm sorry, the union of two. That's exactly what you think about when you've heard the word union used before. At weddings, they talk about this join these two people together and as a union, whatever. Well, that means you're taking two people, jam them together, hoping that they they become one, and for a good long time, right? So that's what we mean by the union. I think you're probably familiar with that, but I'm still throwing that out there in case you're not familiar with that. Let's add to that, kind of along the same lines, the intersection of sets A and B denoted, and we use the same symbol, but we turn it upside down. So A intersect B. This is the set of elements in both set A and set B. And really, if I'm doing this justice, when I talk about the intersection, and is the key word here. When I'm dealing with the union, or is the key word. It's just that we use an inclusive or, where it can be not just possibly an A or B, but both. The intersection is things that are in both, absolutely in both. So if we draw another Venn diagram, set A and set B. When I talk about the intersection, I'm talking about the overlap, right? The intersection of two streets, when you think about it, is where they overlap each other. Oop, wrong styles. Okay, so we're talking about just the stuff right in here. It's kind of the football-shaped region between those two. And again, and is the key word here. And. It has to be in both. Now, what this will lead us to do, when we start talking about proofs later on, when we say something's in an intersection, there's only one place it can be, right? But when we talk about something being in the union, we're going to run into cases. We're going to say, oh, well, if it's in this one, then this happens. If it's in A union B, it's in A, or it's in B. If it's in A, that's one case, we do something. If it's in B, that's another case, we do something. Okay, so the or will lead us to cases, whereas there's only one case here. If we're talking about the intersection, it's present in both sets, and that's it. We also have a little bit of notation I'll throw in. An empty set denoted, and we use a circle with a line through it. Some books use a zero with a line through it, but it's really truly a circle with a line through it. Is a set with no elements. Okay. If A intersect B is the empty set, okay, that means there's nothing in this middle region right here, then we say that A and B are disjoint. Okay, and you know there are certain properties that are nice about the empty set. The one I want to bring up right now is that because when we talk about something being a subset of another, we say, well, anything in this, if it's an element of this, it's an element over here. That means this is a subset of that. It's necessarily smaller, possibly the same size, right? It's like greater than or equal, or I'm sorry, less than or equal. We do have the possibility of things being equal size, right? So with the standard subset notation we use with this and the bar under it, we're allowing for the possibility that they're equal. Okay, but in particular, the empty set is the subset of any set that we deal with. And that may sound strange, but anything that's in the empty set belongs in the other set. It's just that there's nothing in there. Okay, so by default, it fits inside the other set. The empty set is basically like our zero. When we start dealing with whole numbers, it's the zero is what we used to say there's nothing going on there. The empty set is what we say when there's nothing in the set. Okay? All right. The complement and I double checked to make sure I'm writing it right. There's another English word that we use too called complement, P-L-I-M-E-N-T, which means to tell somebody they look nice or to say something nice to somebody. This is complement, as in additional part. We do use that word in the English language, but it means that it somehow completes. If you complement someone else's skills, that means you do the things that they're not able to do, for example. So the complement of a set A, and the notation we use for this, we'll put A, but then we put a bar over the A. Okay? This is the set of elements in the universal set U, but not in A. And again, my key word here is not. For a complement, we think not in A. So if I'm drawing a Venn diagram to kind of illustrate this, with my universal set, really I don't need two sets here, just A. So if I look at things in the complement of A, I look at everything that's not in A, and that's everything outside. Here. So, union or, intersection and, complement not. Okay? And then similar to this, in fact it's very similar to this, is the notion of the difference. The difference of a set B from set A. Denoted A minus B, and we just use the regular subtraction symbol. Okay, this is the set B from the set A. Okay, is the set of elements in A, but not in B. Okay. So again, if I'm drawing a Venn diagram, and I'll get both sets in this time. A universal set. Here's my set A. Here's my set B. If I'm looking at A minus B, or the difference from B of B from A, I take things that are in B. Take things that are in A, but not in B. So I'm looking at all these things that are in A, but not in B. In fact, it really looks like what you're doing. It doesn't have to be the universal set for this to work. For example, here B is not completely contained in A, right? But we still start with the things in A, and then we take anything that's B out of it. Okay, so that gives us this side. In fact, if you'll notice, I'll write it off to the side. Note that A bar is really nothing more than the universal set minus A, right? It's just that A in that particular case happens to be a subset of the universal set. That's not always going to be the case. Okay. So, for example, here, B may not have been a subset of A, but we can still take everything that's in B out of the set A, and that's the difference. Okay. For that reason, though, sometimes we say it's the complement of B with respect to A. Okay, but that's, a little weird, because with complement we are always talking about here's something that's a subset of something else. Okay. Our general types of proofs here, and I'll wrap up today by showing you a proof and how we would do things like this. Really are going to go one of two ways. Okay. We might want to show, you might have a statement like, prove A is a subset, and I shouldn't, let me back up. I don't want to just use A, but, it could be any combination of different sets. So here I'll call it set 1 is a subset of set 2, and these things could be like, combinations with with complements and with unions and intersections, all these kind of things. Okay. Well, in this kind of case, the proof will look basically like this. We'll take something out of set 1. And I'll use the notation that we've seen before. Let X be an element of this set. And then this should look familiar to you. Then dot, then dot, then however many steps it takes. And then finally we'll say, thus X is an element of set 2. If we take a general element out of set 1 and show that it has to be in set 2, what you've proven is that the first set is a subset of the other. Okay, and that you have to take a general element. It can't be a special one. It has to be any element. Take any element out of set 1, then this happens, this happens, this happens, this. Oh, then it must be in set 2. Therefore, set 1 is a subset of set 2. Okay? And that's if we're proving one's a subset of the other. The other thing you'll see is where we want to prove that two sets are equal. So here's set 1. I want to show it's equal to set 2. This is basically the set equivalent of our if and only if proofs, right? When you think about less than and greater than, if I take X and it's less than or equal to Y, and then I look and figure out that Y is also less than or equal to X, then the only thing that's possible there is that X and Y have to be the same, right? Well, it's the same thing here. To show that two sets are equal, we typically don't have a direct way of doing that, like an algebraic way of doing that with sets, but we would set out to prove that first, oh, and I forgot to write my little standard poof. First, let X be an element of set 1. Then blah 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 blah. You know how that goes. And then finally say, then why is not this stuff popping up on my screen? Love to know that. Come on, let's go, man. I somehow lose my connection. Let's see what's going on here. Secure there. Secure there. I knoweth not why the rest of my writing is not showing up. You just refresh it, see what happens. Very interesting, very interesting. Our internet must be down is the only thing I could think of here. So let me pause for just a second and then I'll come back and get this working again. Okay, I'm back. I think our internet just blinked off for a moment or two. I'm not really sure why it did that, but So here we're back. If we're going to prove that two sets are equal, we'll first prove that one set's a subset of the other, so you let X be in set 1, and then show, well, then that means, oops, sorry, it's too big. Then X is an element of set 2, thus set 1 is a subset of set 2. Then let X be a general element in set 2. Then blah 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 blah. And finally we're able to put together then X must be an element of set 1. Thus set 2 is a subset of set 1. Notice how this is kind of like the if and only if statement. Once we have it both ways, that tells us therefore set 1 is equal to set 2. Okay? So the equal statements are going to be a whole lot like our if and only if, where we have to say, well, start with this side, get over here, and then start with this side and get over there. Okay? So let's do an actual proof. So let's prove that if A and B are sets that are subsets of a universal set U, what I'd like to prove is that the complement of the union is equal to the intersection of the complements. Okay, this is actually one of De Morgan's laws. If you were to look this up, you would see that this is named after a mathematician, De Morgan, and there's two of them. The other one would state that the complement of the the intersection of two sets is the union of the complements. Okay, but I'm going to save that one for you as a homework problem. Let's set about proving this. Okay, so here's the way we go about it. I'm going to have to do the double set inclusion. I'm going to have to take something out of the complement of the quantity A union B and show that it's in the intersection of the two complements, and then once that gets me subset one way, and then do it the other way. Start on this side, show that this is a subset of that one. That double set inclusion will say that they're equal. So let's let X be an element of the complement of A union B. Okay. Now what does that mean? Then X, it's in the ballpark, it's in the universal set, but X is not, now, you know, like we have not equal to, we put a line through it, not an element of A union B. Okay? So again, just like when we deal with equalities and in and not equal to, they're not equal to is hard to deal with because we don't know what it is equal to. So what we can do instead is consider, well, okay, suppose it's in A. Okay, and this is where we use a little bit of English. Suppose. In fact, I'll be honest with you, I'm going to go ahead and do it this way. I like to give these proofs a little structure. Not that they have to be. They're in English, so you can certainly write them out in English, that's fine. But they're a little bit easier to follow sometimes if you give them a little structure. So, suppose that X is in A. Well, if that's true, and this is the way we'll show that things aren't in sets. We'll suppose they are and then show that that messes stuff up. Then if it's in A, X would then be in A union B because it's in one or the other. A contradiction. Right, we just said that X wasn't in A union B. So what that tells us then is that X is not in A, or we can say that X is in the complement of A. Right? It's in the universal set, but it's not in A. Okay? Suppose it's in B. Well, once again, that would mean that X is in the union of A and B, which is a contradiction. So X is not an element of B, but it is in the universal set. So we can say that X is in B complement. Then, since X is in A complement, see where we're going with this is I want to show that it's in A intersect B, so I need to show it's in both of them, which I just did. So since X is in A complement and X is in B complement, then X is an element of A complement intersect B complement. Thus, I've established that A union B quantity complement is a subset of the intersection of the complements. Okay, so I've got the set inclusion this way. Now I need to show that A complement intersect B complement is a subset of the other side. Okay, so again, we say now let X be an element of A complement intersect B complement. Now the intersection only gives us one case. It's in both. Then X is an element of A complement and X is an element of B complement. Okay? And again, this is where I like to add a little structures like, oh, well that tells me two things. That means that X is in the universal set but it is not in A. Okay? And this tells me the not in B complement means it's in a universal set. Sorry, I didn't mean to put that complement symbol up there, but what I meant to do was put the line through there, sorry. But we also know that it's not in B, and so X is not in B. Okay? So now you might say, we want to show that it's over here now. So again, you might think about, when you're trying to show that something's in a complement, you might do it by contradiction, say, well, suppose it's in there. Okay? Then X would be in A, or it would be in B. But I've just shown that it's actually not in either one of them. So this is a contradiction. Okay. Thus X is not in A union B. There we go. Thus, we're almost there. We just need to wrap it up. Thus, we know that A complement intersect B complement is a subset of A union B quantity complement. Now, that gets us the set inclusion back the other way. The last thing we say is, therefore, A union B quantity complement is the same as A complement intersect B complement. Okay, due to the double set inclusion. Okay? You're going to see proofs that kind of run that gamut. And the way we handle them is just kind of break them down. I have to admit, it is a little systematic. This is more of the formulaic kind of thing. But you do need to pay attention. It is a slightly different brand of proof than what we were doing earlier. Okay. It will help us though when we start to talk about. We'll eventually talk about functions and relations, and how functions apply to sets. So once we do that, we'll again start to be talking about sets again. So we're not going to just do this and throw it away. We'll end up doing this quite a bit. The homework for this collection of problems is actually posted on Blackboard, and it's I forgot exactly what I called it, but the sets supplement. I think there's 18 problems there, so that'll keep us busy for a little while too. If these go well, and let me wrap up with what I'm going to say today with the complement. I thought people today in class did a great job for their first time at the board. I was really impressed that people were they had done the problems, they had done them well for the most part. A few little minor mistakes, which we were able to to correct, hopefully in a nice, non-threatening way. I haven't actually laughed at anybody. I thought today the students that went to the board did a great job. So, and I just want to see us keep doing that. You watch for me to encourage you to be bold enough to step up and work a problem. I'll be honest with you, if you've not tried a problem previously on paper or at least looked at it and figured it out somewhere, I don't want you going to the board and just foundering around with it, okay? But work the problems ahead of time, try to work them ahead of time, get a feel for why they are what they are, and then look for all of us to kind of encourage you to get up there. It's not a walk of shame or anything to go up, but I do want to kind of build that. I think the only way you do this is you just kind of keep doing it, and eventually these things just kind of come naturally to you. Okay, so I'll post that homework set in the content area of Blackboard. And you can start working on those problems too. Finish up the ones we're doing in 2.1. Certainly if I didn't call your name today, you can almost count on me calling it Thursday. And then we'll go back and see if those folks that kind of took a pass today, I'll go back, give them another chance, and then we'll move on to a new cycle. Okay? All right, that is it for me. I will also post these notes, and work hard, and let's keep doing well. All right, see you.